In this video, we are going to look at how we can use vectors to calculate distances between objects in three-dimensional space. Now, first of all, we just need to have a quick way of ensuring that we know that we can find an acute angle. And the result we're going to be chasing for is that the formula cos alpha equals the modulus of the scalar product of A dot B divided by the length of A times by the length of B will always give us the acute angle between the two vectors A and B. And we're going to find this result useful in both this video and the next one. So let's try and see why this result is true. We already have seen how the scalar product can be used to give us the angle between two vectors. We know the scalar product is defined by A dot B is the length of A times the length of B times the cosine of the angle between the two vectors. So the cosine of theta is equal to A dot B divided by the modulus of A times by the modulus of B. Now, if A dot B is positive, then that means we've got cos theta is a positive number because we've got a positive divided by a positive. So therefore theta will be an acute angle. So we've got the acute angle is actually theta. So we've got alpha is the same thing as theta. So we've got cos alpha is A dot B over the length of A times the length of B. But with A dot B being positive, A dot B is exactly the same thing as the modulus of A dot B. So there's no problem if A dot B is positive. What about if A dot B is negative? Well, if A dot B is negative, then the expression cos theta equals A dot B divided by the length of A times the length of B means that cos theta is a negative number, and hence the formula cos theta equals A dot B over length of A times the length of B is going to give me an obtuse angle, not an acute angle. So we might be in the position where A and B look like this. We've got an obtuse angle between A and B, and the acute angle between the directions of A and B is going to be the angle alpha, where alpha is 180 minus theta. Now, the cosine of alpha is the cosine of 180 minus theta. The cosine of 180 minus theta is cos 180 cos theta plus sine 180 sine theta. Cos of 180 is minus 1. Sine of 180 is 0. So cos of 180 minus theta is minus 1 times cos theta plus 0 times sine theta, which is just minus cos theta. But cos theta is A dot B over the length of A times the length of B. So we've got minus cos theta must be minus A dot B over length of A times the length of B. But A dot B is a negative number in this case, which means that minus A dot B is precisely the same thing as the modulus of A dot B in this case. So in both cases we've seen that the formula modulus of A dot B divided by the length of A times by the length of B gives us cos alpha, where alpha is the acute angle between the directions of A and B. Okay, our first distance result is going to be to find the perpendicular distance of a point from a line. So, Let's suppose that we've got the line r equals ABC plus s times UVW. So UVW is the direction vector of the line, and we wish to calculate the distance of the point P, whose coordinates are PQR, from this line. Well, what we need to do is we need to drop a perpendicular from P down to the line, and then we can set up a right-angled triangle consisting of A, the point P, and the foot of the perpendicular. And if we can calculate the angle alpha lying between AP and the line, in other words, alpha is the acute angle between AP and the direction vector UVW, then we've got D is equal to AP sine alpha. So we're basically saying we need to draw ourselves a sketch. We need to calculate the acute angle alpha between the vector AP and the direction vector of the line. And once we've done that, we simply need to calculate D as being AP sine alpha. So let's see this in the case of an example. So we've got to find the perpendicular distance of the point 5, 4, minus 2 from the line passing through the points 1, 2, 0 and 4, 0, 1. So there's my picture. The perpendicular bisector from P to the line I've drawn in, and I'm going to put in the vector A to P. Now A to P, in moving from A to P, I've gone from 1 to 4, 5 in the x direction, so that's an x move of 4. From 2 to 4 in the y direction is a y move of 2. And we've gone from 0 to minus 2, which is a z move of minus 2. The direction vector for the line is A to B, and the vector A to B has an x move of 3, a y move of minus 2, and a z move of 1. So we've got the direction vector for the line is the vector 3, minus 2, 1. Now if alpha is the acute angle between AP and the direction vector of the line, then we know that cos alpha can be found by taking the modulus of the dot product of AP and the direction vector, and then dividing by the magnitude or the length of AP times by the magnitude or length of the direction vector. So the scalar product, it gives me 4 times 3, which is 12, plus 2 times minus 2, which is minus 4, plus minus 2 times 1, which is minus 2. So the scalar product is 6. So I've got the modulus of 6, which is 6 on the top. On the bottom, I've got to calculate the magnitude of the vector 4, 2, minus 2, which is the square root of 4 squared plus 2 squared plus minus 2 squared, which is root of 24. And multiply that by the length or the magnitude of the vector 3, minus 2, 1, which is the square root of 3 squared plus minus 2 squared plus 1 squared, which is the square root of 9 plus 4 plus 1, so that's the square root of 14. So I've got cos alpha is equal to 6 divided by root 24 times root 14. Using my calculator now, that tells me that alpha must be 70.89 degrees. And then just using our right angled triangle, we've got that D is the same thing as the length of AP times sine A. We've already worked out that the length of AP is the length of the vector 4, 2 minus 2, which is root 24. So I've got root 24 times sine alpha, which gives me 4.629. Now it's just worth commenting that in a previous video, this Vectors 2 video, in example 5, we found an alternative method of finding the distance of a point from a line. If we've got two parallel lines, we can use exactly the same method as we've just done to find the distance between the two parallel lines. And again, the best thing to do is to start with a sketch diagram. So we've got the two lines. The first line is has equation r equals 1, 5 minus 2 plus s times 2, 3 minus 2. And the second line has an equation of r equals 393 plus t times minus 4, 6, 4. So we can see that the two lines are parallel to each other because minus 4, 6, 4 is just minus 2 times 2, 3 minus 2. Now let's just draw a sketch then. Suppose this is my line L1, which passes through the point 1, 5 minus 2 and has got a direction vector of 2, 3 minus 2. And here's the line L2, which passes through the point 3, 9, 3 and has got a direction vector of minus 4, minus 6, 4. Now we can create a right angled triangle for this picture fairly easily, because what we want is the distance between the two parallel lines, and we can certainly say that that is the distance of B away from L1. So the right angled triangle we're going to be considering is a triangle consisting of A, B and the line L1. And provided we can find that acute angle alpha between A, B and the direction vector of L1, then D is simply AB sine alpha. Now the vector AB has an x move of 2, a y move of 4 and a z move of 5. So AB is the vector 2, 4, 5. The angle alpha is the acute angle between AB and the direction vector of the line, which is 2, 3 minus 2. So we've got cos alpha is the modulus of the scalar product of 2, 4, 5 and 2, 3 minus 2 divided by the length of the vector 2, 4, 5 times by the length of the vector 2, 3 minus 2. The scalar product gives me 4 plus 12 plus minus 10, which just gives me 6. The length of the vector 2, 4, 5 is the square root of 2 squared plus 4 squared plus 5 squared, which is root 45. And the length of the vector 2, 3 minus 2 is the square root of 2 squared plus 3 squared plus minus 2 squared, which is root 17. So we've got cos alpha is equal to 6 divided by root 45, root 17. Now the question says that we've got to work exactly in this question. If it hadn't said that, then we would have continued by simply using our calculator to find alpha to a suitable level of accuracy, and then we would have said that D is AB sine alpha. We already know that AB has got length of root 45, So it would just be d equals root 45 times by the sine alpha, gives me 6.548. But in this example, we're being asked for an exact value for the distance of between the two parallel lines. So what we need is an exact value for sine alpha. We know an exact value for cos alpha. Well, that's easy enough. We can just use the fact that we know that sine squared alpha is 1 minus cos squared alpha. 1 minus cos squared alpha is 1 minus 36 over 765. So I've got 1 minus 36 over 765, and we can certainly use our calculate the fraction fraction facilities on our calculator to see that that simplifies down to 81/85. So sine alpha is going to be 9 over root 85. It can't be minus 9 over root 85 because alpha is an acute angle. So we can now say that the distance that we're looking for is AB sine alpha. So that is root 45 is the length of AB times by 9 over root 85. And again, if we use our calculators, they will probably tell us that that comes through to be 27 root 17 over 17. We now consider the problem of finding the perpendicular distance between two skew lines. So suppose that I've got lines L1, which has the equation R equals A plus SU, and L2 is R equals B plus TV. And that A and B are the points whose position vectors are little a and little b respectively. Now, we're going to suppose furthermore that the vector n is perpendicular to both u and v. So the vector n is perpendicular to both the direction vectors. If P and Q are the 2 points on L1 and L2 respectively, which are closest to each other, then P must be the foot of the perpendicular from Q to the line L1. And that tells me that the vector QP must be perpendicular to the direction vector of L1. So the vector QP must be perpendicular to U. Moreover, Q will be the foot of the perpendicular from P to the line L2. And that tells me that PQ, the vector PQ, must be perpendicular to the direction vector V of L2. So the vector PQ must be perpendicular to V. Now this means that the vector PQ is also perpendicular to both U and V. And this means that the two vectors PQ and N must be parallel to each other. So we know that the vector PQ must be some multiple of the vector N. So we know that N is perpendicular to both U and V, and we know that P to Q is some multiple of N. Now, since P is on the line L1, we can say that there's a value S, such that the position vector of P, that is OP, is equal to A plus S times U. And similarly, since Q is on the line L2, there's a value T such that the position vector of Q, that's the vector OQ, is equal to B plus TV. Now, we know that K times N is the same thing as the vector PQ for some value of K. And we're going to try and find what this value of K is. PQ is the same thing as the movement from P to O and then from O to Q. P to O is just the opposite of O to P, so that is minus O to P plus O to Q. So I've got P to Q equals minus OP plus OQ, so that's minus A plus SU plus B plus TV. In other words, I've got minus A minus SU plus B plus TV as my description of the movement P to Q. Or I've got K times the normal vector is equal to minus A minus SU plus B plus TV. Now the really cunning part of this proof is that we are going to take the scalar product of the left hand side and the very far extreme right hand side. And we're going to take the scalar product of both sides with the vector n. So the left hand side becomes k times n dot n. The right hand side is going to become the scalar product of minus A minus SU plus B plus TV dot n. Now we'll multiply out the bracket. So we've got k times the scalar product n dot n equals the scalar product minus A dot n minus S times U dot n plus B dot n plus T times V dot n. And there's two really important observations we're going to have to make. First of all, n dot n is the length of n times the length of n times the cosine of the angle in between n and n. Well, the angle between n and n is just 0. So n dot n is the length of n times the length of n times by cos of 0. In other words, n dot n is the length of n squared. And the second observation we need to make at this stage is that we know that n is perpendicular to both u and v. So that means the scalar product of u with n and the scalar product of v and n, both of those have to be equal to 0. So we've now got the left hand side just becomes k times by the length of n squared, and the right hand side just becomes minus A dot n plus B dot n, or in other words, B minus A dot n. And this enables us to say that k must be the scalar product of B minus A dot n divided by the length of n squared. Now what we're after is the size of the vector PQ. We're looking for the distance of P from Q. So the distance of PQ is the size of the vector k times n, which is just going to be the modulus of k times by the length of n. So that's the modulus of B minus A dot n divided by the length of n squared times, that's the value of k, times by the length of n. The length of n is going to cancel with the length of n squared on the denominator of our fraction. So we're going to end up with simply the modulus of B minus A dot n divided by the length of n. And this now gives us the strategy for finding the perpendicular distance between two lines. We first of all need to find a vector n, which is perpendicular to both the vectors u and v. Having found that vector n, we can say that the required distance is given by the formula d equals the modulus of the scalar product b minus a dot n divided by the size of the vector n. And that formula is given in the WJEC formula booklet. So let's see this actually in practice. So we're going to find the perpendicular distance between the lines r equals 1, 5 minus 2 plus s times 2, 3 minus 2 and the line r equals 3, 9, 3 plus t times 1 minus 1, 2. The first thing we've got to do is we've got to find a vector which is perpendicular to the two direction vectors. So we need a vector which is perpendicular to both 2, 3 minus 2 and 1 minus 1, 2. Let's suppose the vector alpha, beta, gamma does the trick for me. Then alpha, beta, gamma dot 2, 3 minus 2 must equal 0, means that I've got 2 alpha plus 3 beta minus 2 gamma must equal 0. Similarly, alpha, beta, gamma has got to be perpendicular to 1 minus 1, 2. So I've got 1 minus 1, 2 dot alpha, beta, gamma equals 0, which tells me that alpha minus beta plus 2 gamma equals 0. Let's shift the gammas onto the other side. So we've got 2 alpha plus 3 beta equals 2 gamma as my first equation. And as our second equation, we've got alpha minus beta equals minus 2 gamma. So if we take equation 1 and add 3 times equation 2, we will eliminate the betas and we will obtain the result that 5 alpha is minus 4 gamma, which tells me that alpha is minus 4/5 gamma. Inserting that into equation 2 now tells me that I have got beta must equal alpha plus 2 gamma, which is 6/5 gamma. And if I choose to put gamma equals 5, just so that I get nice integer values for alpha, beta and gamma, then I get a normal vector of minus 4, 6, 5. Now, little a is the position vector of the known point on the first line. So that's 1, 5 minus 2. Little b is the position vector of the known point on the second line. So we've got a is 1, 5 minus 2, b is 3, 9, 3, and we've just calculated that the mutual perpendicular to the two lines is the vector n, which is minus 4, 6, 5. So the distance between the two lines is given by the formula the distance equals the modulus of the scalar product b minus a dot n divided by the size of the vector n. So we've got to calculate first of all the value of b minus a. So that's 3 take away 1 for the x coordinate, which is 2, 9 take away 5 is 4, and 3 minus minus 2 is 5. So b minus a is the vector 2, 4, 5. That has to be scalar producted with minus 4, 6, 5. We need to take the modulus of that answer and then divide it by the length of the vector n, or the magnitude of the vector n, which is the square root of minus 4 squared plus 6 squared plus 5 squared. Doing the scalar product, we've got 2 times minus 4 is minus 8, plus 24, plus 25. So that gives me altogether 41. And when we take the modulus of 41, we just get 41. Square root of minus 4 squared plus 6 squared plus 5 squared is the square root of 16 plus 36, which is 52, plus the 5 squared gives me the square root of 77. So the distance between the two lines is 41 divided by root 77. We're now going to look at how we calculate the perpendicular distance of a point away from a plane. So suppose we've got the point P with coordinates u, v and w, and that we're looking at the plane r dot n equals alpha. So the plane has got a normal of n, and if A is a point on the plane and little a is the position vector of this point, then we know that the scalar product of A with n must be equal to alpha, because r dot n is equal to alpha for all points on the plane. So, if we drop a perpendicular from P down to the plane and let F be the foot of that perpendicular, and we set up a triangle consisting of A, F and P, and what we are trying to calculate is the distance PF. And that triangle is a right-angled triangle because FP is going to be parallel to n, and we know that n is at right angles to any vector in the plane, and AF is a vector in the plane. If we let theta be the acute angle APF, then chasing round our angles, theta is also the acute angle between n and the vector AP. What we are looking to calculate is PF, and PF is the same thing as AP times cos theta. But AP times cos theta is the same thing as AP times the length of n times cos theta divided by the length of n. Now the reason we've done that is that AP times the length of n times the cos theta is precisely the scalar product of AP with n. And since we're insisting that theta is the acute angle between AP and n, we'll put the modulus signs round just to be safe. So we've got PF is AP times the length of n times cos theta divided by the length of n. That's the same thing as the modulus of the scalar product of AP with n divided by n. Now, AP, the movement from A to P, is equivalent to moving first of all from A to O and then from O to P. A to O is the opposite of O to A, so A to O is minus A, and O to P is simply the position vector of the point P, which we'll write down as being little p at the moment. So we can now say that D is the modulus of the scalar product of minus A plus P with n divided by the size of the vector n. Multiplying out the brackets inside the modulus, we get the modulus of minus a dot n plus p dot n, all divided by n. Now we need to remember at this stage that A is a point on the plane, and therefore a dot n is simply going to be alpha. So we've got now p dot n minus alpha to take the modulus of and then divide by the size of n. So we've now got the result that the distance is the modulus of p dot n minus alpha all divided by n. We're now very close to our result. If we want the perpendicular distance of UVW from the plane whose Cartesian equation is n1x plus n2y plus n3z equals alpha, that Cartesian equation can be written in vector form as xyz dot n1, n2, n3 equals alpha, or r dot n equals alpha, where n is the normal vector consisting of n1, n2, n3. Now, from what we've just done, we found out that d was the modulus of p dot n minus alpha divided by the size of n. Now, p dot n is simply UVW dot n1, n2, n3. And the size of n is simply the square root of n1 squared plus n2 squared plus n3 squared. And if we evaluate the scalar product, then what we end up with for our expression for d is that it is the modulus of n1u plus n2v plus n3w minus alpha over the square root of n1 squared plus n2 squared plus n3 squared. Now, fortunately, this formula is given to us in the formula booklet and is in fact very easy to use. So for our final example, we're going to find the perpendicular distance of the point 3, 1, minus 5 from the plane 3x minus 2y minus 4z equals 8. So there's the output from the formula booklet. So we can say that the distance is going to be the modulus of 3 times 3, take away 2 times 1, take away 4 times minus 5, minus 8, divided by the square root of 3 squared plus minus 2 squared plus minus 4 squared. And that gives us 19 over the square root of 29 as the distance of the point 3, 1, minus 5 from the plane 3x minus 2y minus 4z equals 8. So, I'd like you at this stage to just pause the video and have a go at these questions. And when you've done that, you'll be pleased to hear you've actually finished the work on this particular section, where we have been looking at how vectors can be used to find distances between objects in three-dimensional space.